So, students, we have already discussed the classical harmonic oscillator, and what we have seen that the energy of this classical harmonic oscillator is continuous, and it goes to infinity. Now, in this video, I'll be talking about the same harmonic oscillator, but here we will subject this harmonic oscillator to the quantum mechanical treatment. So here we have quantum mechanical treatment of harmonic oscillator. That should be the case. Now, I would certainly start from the Schrödinger's wave equation. I would like to write down Schrödinger's wave equation in one dimension, in a dimension of x. So writing down Schrödinger's steady state equation as d2 psi by dx2 plus 2m by h cross square e minus v of psi equals 0. Now, this is the Schrödinger's wave equation, and this V represents the potential energy, and this V represents the potential energy, and we can obtain the expression for this potential energy as V is equal to 1/2 of kx square. And this thing can be done in a very easy way. You can use a classical harmonic oscillator. We can have the restoring force equal to minus kx. Then all we have to do is to calculate the work out of it. So when I substitute this potential energy term in the Schrödinger's equation, it becomes d2 psi by dx2 plus 2m by h cross square e minus 1/2 of kx square psi equals 0. So what we have done is we have introduced the term V in terms of the potential energy of the harmonic oscillator. So moving from here, what should we do is we should be using some substitutions, and if we go with this 1/2 of kx square, we can rightly have this k as m omega square, because we have omega square equal to under root of k by m. So if we have to calculate k, so this should be omega. Yeah. So if we have to calculate k, we will square it, and we will get k is equal to m omega square. So squaring this will give me k by m, and so k will be m omega square. So if that's the case, I can think of using for k here, what I will get is 1 by 2. Instead of k, I have m omega square, then I have original x square. So I can use this in the original equation, which I wrote down. That's d2 psi by dx2 plus 2m by h cross square times e minus 1 by 2 m omega square x square. Then we will have psi equal to 0. There should be no problem with this. Now, what would I like to do is I will incorporate this 2m by h cross square into the bracketed term. So I will have d2 psi by dx2 plus 2m e psi by h cross square minus. Then we can see here we will have the cancellation of 2 and 2. What we will have is we will have m square, because m and m will give me m square. Then I will have omega square. Then I'll have x square by h cross square. and I can have a bracket for it, psi, this is the rough, equal to 0. All right. Now let's go with some substitutions for this, and let's use some kind of formalism, like let me introduce a constant alpha. This alpha I will choose as m omega by h cross, and I will choose beta, and this beta I will choose as 2me by h cross square. And what we'll do is that we will substitute for alpha as m omega by h cross here, and for beta 2me by h cross here. So what we will have in the Schrodinger's equation, we will have what we will have is we will have d2 psi by dx2 plus, yeah, there I will have beta, then I can use minus, that is alpha square x square times psi equal to 0. That should be the case. Okay, that thing I have already explained. Very simple substitution is out here. Now, in order to solve this equation, let's go for another substitution to make this equation more consistent, to make it more convenient. Now, let me use what should I use? I will use that under root of alpha times x is equal to y. All right, and this is this equation where I choose under root of alpha x equal to y. So what can I do here is that this alpha is a constant, and I can write down this in x under root of alpha, and I can find the dy by dx from this. So dy by dx will be under root of alpha. That should be clear. And if I write down d psi by dx, and I can write down this d psi by dx as d psi by dy times dy by dx. There should be no problem with it. So for this dy by dx, I can use under root alpha. So what will I come up with is this d psi by dx will be under root of alpha d psi by dy. This should be the case. And I can immediately look for the double derivative of this psi. I will call this 4, and I would like to go for the double derivative of this psi. So what I will have is d2 psi by dx2. I can write d by dx of d psi by dx. So d psi by dx. That should be the case, and I can replace here for I can replace here for d by dy. Yeah, that should be the case. Yeah, I can replace here for d by dy, and what I will have is under root alpha. Then I will have d psi by dy times dy by dx. And this thing is already evaluated as under root alpha d psi by dy, right? So what we have is, what we are trying to write here is d by dy of under root of alpha. Then we have d psi by dy, and then we have dy by dx. And what we will have is for this thing, am I right here, d psi by dx, and this is, yeah, d psi by, so for d psi by dx, for d psi by dx, what I started from, I'm taking the double derivative of this, and for this I am taking under root alpha d psi by dy. That's correct. Okay, under root d by dx of under root of alpha d psi by dx, and I'm multiplying this by dy so that I have d by dx. So this is dy times dy by dx, and I think we already have dy by dx that's here, that is under root of alpha. So I can immediately write down that this is under root of alpha into under root of alpha will give me under root alpha whole square, and what will left, I'll be left with d2 psi by dy2. That should be the translation. Yeah, that's correct. Okay, so what we have d2 psi by dx2 now. Now, if we substitute this double derivative of psi with respect to x in the original equation that we have, so I would like to call this 2, I would like to call this as 3. So substituting 3 in 2, what are we going to get? We are going to get alpha. It is not square, it has to be alpha. It's under root alpha into under root alpha. This is going to give me alpha only. So I will have alpha, then I will have d2 psi by dy2 plus, then beta minus alpha square, then beta minus alpha square. But I have to resolve this x square. Now where is x? What will be x square? X square will be y square by alpha. So this is y square by alpha times the original psi equals 0. That should be the case. So this alpha and square is going to cancel, and what we are left with is, and I would like to bring down this alpha down, and what will I find is I will find d2 psi by dy2 plus, it will be beta by alpha, then minus y square. This alpha will go with this alpha, and times psi equals 0. This should be the case. And now, in order to get some acceptable solution of this differential equation, if for the sake of argument, if I assume, what should I try is the asymptotic solution. So by assuming that this y that I have, if this is very, very greater than beta by alpha. And in this case, the term beta by alpha can be neglected from this equation. So what we will have is, so I will call this equation as equation A. So what will be left with d2 psi by dy2 plus, it will be minus simply y square psi is equal to 0. And we can have the solution of this equation, and we can have its solution psi equal to e to the power of plus minus y square by 2. Now, if we think that certainly we are proposing here two possible solutions for this differential equation, but if we go with the probability density, if we take the psi star, that gives us the probability of finding the particle somewhere along the x-axis that we have chosen. Therefore, it must decrease continuously to 0 as x in the original equation tends to minus infinity, and x tends to plus infinity. So what's the case here is that the solution for positive, if we think of the solution for positive like e to the power of plus y square by 2. This solution will increase rapidly with increasing y, and hence that's going to increase x. So if x increases exponentially, that means at infinity what's going to happen is that the value of y will tend to be 0, and automatically the solution to be chosen as e to the power of plus y squared by 2 is not correct. Therefore, this solution that psi equals e to the power of plus y squared by 2, because it's a function that's rapidly increasing. This cannot be the acceptable solution for the function. So what should be taken as acceptable solution here is that should be taken as psi equal to e to the power of minus y squared by 2 as y tends to infinity. So this will be the solution. This will be the only acceptable solution to the differential equation that we have. Now, if we go with the standard procedure for solving the differential equation, the like of this, so what is needed here is that this equation that we have it's valid for all the values of y. This equation is valid for all values of y. So what we have to try here is we have to try a solution of the form psi is e to the power of minus y squared by 2 h of y, where this a is a constant, this a is a constant, and h of y that we have introduced here, it's a polynomial. It's a polynomial in y, and this h of y is known as Hermite polynomial. Hermite polynomial. All right. So in order to determine this Hermite polynomial, what we have to do is we would like to differentiate this equation, and when we differentiate this equation, say this is equation 3. So differentiating, and what we find is d psi by dy, it will come up as minus a e to the power minus a. Then we will have minus this a. So what we are trying to do is that we have to use uv form here. Okay, so in doing that, what am I going to get is I will have y. I will have y e to the power of minus y squared by 2. Then I will have h as its, then plus I will have a e to the power of minus y squared by 2 as its, then dh by dy. That should be the case. So in the first case, what we do is we differentiate e to the power of minus y squared by 2. So it will remain as its. Then we take the internal derivative of minus y squared by 2. So that will be 2. That will be minus 2y by 2. So 2 and 2 will cancel, but we will have minus out. So here we will be left with y. That should be the case. And again, what we have to do, we will again differentiate this. So again, differentiating. A bit of homework, and you can do it. You can do it better than me. And so going with d2 psi by dx. Sorry, it's y by dy2 is gonna give me. Okay, it will give me minus a e to the power of minus y squared by 2h plus I will have a y squared e to the power of minus y squared by 2 and then I will have h, and then I will have minus a y e to the power of minus y squared by 2. Then I will have dh by dy, and then I will have minus a y e to the power of minus y squared by 2 dh by dy, and then finally I will have plus a e to the power of minus y squared by 2 d2h by dy2. In both the cases, we have taken the UV rules, and precisely simple and can be done. Now, this whole thing, what we have to do is we would like to substitute this in our original equation that we have in terms of y. So this is a, and I would like to substitute this b. So substituting b in a that we have. So all I have to do is to use it here. So what am I going to get is, one thing is clear, that I have a common to everything. E to the power of minus y squared by 2 is common to everything. What I will be left with is h. This minus h will be there, and then I will have plus y square, h will be there, and then I will have a doubling of this thing. This will give me minus 2y dh by dy, and then finally what I'll be left with is plus d2h by dy2. I'll close it. Then I have what I have then is beta by alpha minus y squared times times, here I will have for psi the same thing that I have for psi here that I have chosen. So what is that? So a e to the power of minus y squared by 2 will be out from that also. So here I will be left with h, this Hermit, the function Hermit polynomial, and this thing is going to be equal to 0. Now this whole thing that's common for both is not equal to 0. So what we have equal to 0 is we have d2h by dy2 minus twice y dh by dy plus beta by alpha. This y squared term is going to it's going to die with this minus y squared term. Then what we will have is here is h common. You should keep that thing in mind. This is multiplied by h, and this whole thing is also multiplied by h, and what will be left with beta by alpha minus 1 times h is equal to 0. It has become a little bit messy here. I'm sorry for that, but I don't have any alternative. So moving on from here, what we have is we have a differential equation in terms of this Hermit polynomial, and what would I like to do here is that I would assume that this beta by alpha minus 1 is equal to some 2n. Okay, so what am I assuming is that beta by alpha minus 1 is equal to 2n. So what does that imply? That implies that beta by alpha is 2n plus 1. There should be no problem with that. And so how can I write down this equation then? Then this equation is going to be d2h by dy2. This is minus 2y dh by dy. Then I will have plus for beta by alpha minus 1, I'm taking 2n. I'm taking 2n, then 2nh. Okay, this is equal to 0. Now, this is the standard, what we call this as, this is the standard mathematical equation, and this equation is known as Hermite equation. We call this equation as Hermite equation. And the solution solution of these equations are called as Hermite polynomials. So the solution of this equation are called as Hermite polynomials. And 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 the generating function for Hermite polynomials is hn of y is equal to minus 1 whole to the power of n e to the power of y square d raised power n by dy raised power n times e to the power of minus y square. Okay, so now let us go with the constant. Now only those solutions for this equation are acceptable whose values for y are such that this beta by alpha is equal to 2n plus 1. So only those are the acceptable solutions of this differential equation, this Hermite equation. So for that case, what I have is beta by alpha is equal to 2n plus 1. Now I have already used some specifications for beta is basically 2me by h cross square, and alpha is if you rightly remember, it is m omega by h cross. So what will be beta by alpha here? So beta by alpha will be 2me by h cross square times h cross by m omega. So this m and m is going to die. This h cross and square is going to get out of this, and what we'll be left with is 2e by h cross omega. So what we can say is that this 2e is it is simply h cross omega times, what is this, beta by alpha? That's 2n plus 1. This is 2n plus 1. And E can be calculated as h cross omega times n plus 1 by 2. Now this equation gives me the allowed energy levels, that this harmonic oscillator can have only certain possible energy levels, right? And we can see here that this energy of any level that can be h cross omega times n plus 1 by 2. And to be sure here is that this equation gives us basically it gives us the eigenvalues, it gives us the eigenvalues, or you may also call them as permitted values of total energy for the harmonic oscillator for n is equal to 0, 1, 2, and 3, and so on and so forth. And these energies are discrete energies. These are discrete energies that we have, and we can again write down this is E is h nu times n plus 1 by 2. For that we can use this h cross omega. So this is h by 2 pi times 2 pi nu. So 2 pi and 2 pi cancels. So this h cross omega that we have is giving us h nu times n plus 1 by 2. That's the case. So what's going to happen here is that we have discrete values for energy. And we have the corresponding energy levels for that, and we can see if we have to draw something in terms of energy levels, is we have the energy level for n is equal to 0, for n is equal to 1, n is equal to 2. They are equally spaced lines. So here this is for n equals 0, this is n equal to 1, this is n equal to 2, and this is n equal to 3. Okay, so in every case we have a difference of energy h nu, we have a difference of energy h nu, we have a difference of energy h nu. So here we have energy at n equal to 0, that's 1 by 2 h nu. Then here automatically we will have 3 by 2 h nu. Then here we will have 5 by 2 h nu. And then here we will have 7 by 2 h nu. Now the energy of this harmonic oscillator is quantized. It is quantized in the steps of h nu. And the energy levels are equally spaced with the separation between the adjacent levels, and that separation is equal to h nu. Now, when n is equal to 0, so when n is equal to 0, still we have an energy, what is called as the lowest possible energy. That means this harmonic oscillator can have energy even at absolute zero, and that energy is going to be 1 by 2 h nu. And this value of energy, this lowest value of energy, is known as zero point energy. Okay, so what we find is that according to quantum energy, the energy of the harmonic oscillator is quantized. It's quantized in the steps of h nu. And with its lowest possible energy as 1 by 2 h nu. This is certainly in contrast to the classical theory, which we have done in classical harmonic oscillator, where we found that the energy of the oscillator is continuous. It is continuous from 0 to infinity. And that's the case.